Um, so welcome for the final session of this Eurocrypt. So we'll have the pleasure to talk of cryptanalysis right now. And our first speaker will be Deepayan Das from NTT Social Informatics Laboratories, and he will present us a key recovery attack on the partial Vandermonde knapsack problem. So Deepayan, the floor is yours.
Hello, everyone. So I will be talking about key recovery attack on the partial Vandermonde knapsack problem, and this is a joint work with Antoine Zhu. Okay, so the central assumption for doing lattice-based cryptography is this low-density inhomogeneous CIS problem, or the LWE problem. The problem informally states the following. Given a fat matrix A and a vector B, which is basically A times some small vector little f, mod q, and the problem asks to find this small vector f. So in this talk, I will be mainly focusing on f, where the coefficients are between the interval -1 to 1. Okay, for practical efficiency, what we do is we use algebraic variants of the matrix. So one such assumption was this partial Vandermonde knapsack problem, where they used some algebraic variant of this low-density SIS problem. In this talk, I will show that a fraction of keys that were proposed in the literature are weak. To start with, first, let's define a ring RQ, which is defined by a defining polynomial, little g of x, which is equals to x to the power n minus 1 when n is prime, or x to the power n plus 1 when n is a power of 2. So these two little g of x were used in the literature, so I'll only fix into these two cases. We want the prime q of a very specific form, where this little g of x splits linearly over the finite field fq. For that, when n is prime, we can choose q of the form 1 mod n, and when n is a power of 2, we can choose q of the form 1 mod 2n. Okay. Let capital omega be the set of all primitive roots of little g over the finite field. By primitive roots, I mean for the first case, we avoid the root 1, and any other root are going to be primitive by definition. Then, for defining the partial Vandermonde knapsack problem, or the PV knapsack problem, what we need are two things. First, a set capital omega t, which is a uniformly random subset of capital omega with t distinct elements. Second, a hidden polynomial little f of x, whose coefficients are sampled uniformly at random with ternary coefficients. The problem is the following. Given the ring RQ, capital omega t, and t many evaluations of the hidden polynomial, find the hidden polynomial when t is approximately close to n by 2. So the problem was initially called partial Fourier recovery problem, and was introduced by Hopstein, Pippa, Schwank, Silverman, and White for doing some post-quantum signatures. After that, this assumption was used in some other work for doing post-quantum cryptography, including encryptions and signatures and multi-signatures. Okay, how to connect this partial Vandermonde knapsack in terms of this inhomogeneous ICs problem? Well, we can view a matrix which is Vandermonde in nature, whose ith row is given by the evaluation of little omega, for little omega belongs to the set capital omega t. And the vector b is now the evaluations of the hidden polynomial, which is known as a part of the problem. Okay. So going from inhomogeneous to homogeneous is quite easy. Like, we just include the evaluation inside the matrix. Now, instead of looking for a vector little f, we are now looking for a vector little f concatenation with -1. And in the right-hand side, you have this null vector. So in lattice terminology, this problem is to find some short vector on the kernel lattice generated by this matrix V with the evaluation vector. And this lattice has dimension n plus 1. And because it's a Q-ary lattice, its volume is q to the power t. Now, from the last slide, we know this F concatenation with -1 belongs to this kernel lattice. And since the coefficients of little f has only -1, 0, and 1, we have the norm of this vector to be approximately close to square root of n, which is unusually short for a lattice of similar dimension and volume. For example, if we see the Minkowski's theorem, it tells that the shortest vector is going to have a norm much larger than what this norm is asking to find. Okay. So at Crypto 22, BGP proposed a key distinguishing attack on this partial van der Moor knapsack problem. And to see this attack, we need to see this partial van der Moor knapsack problem as an instance of the BDD problem. So let Z be any random target for this for the BDD problem, and then for a PV knapsack instance, we know that there exists some lattice vector, which is a query kernel lattice generated by the matrix V, such that it is very close to the target. Algebraically, this lattice vector belongs to the ideal, which is generated by the product of x minus little omega. If we can find some u prime in the complementary ideal of I omega t, which is small, then for a PV knapsack instance, this product of u prime with the target z is going to give somewhat small element in the ring. But for a uniform instance, it's highly unlikely. And that's how we get a distinguishing attack on this problem. The main contribution of BGP is that there is some algebraic way how we can reduce the cost of finding this u prime on the ideal, complementary ideal. For that, if we consider capital omega 2 T1 as the largest subset of capital omega T that remains invariant under the transformation of inverse, then the complementary set of capital omega 2 T1 is also invariant under the transformation of inverses. So if T1 is not too small, then the PV knapsack problem over capital omega T reduces to over capital omega 2 T1. And this condition on T1 is basically for the fact that we don't want the lattice to get too much sparse, not too much dense. Okay. So for finding such u prime inside this complementary ideal of capital omega 2 T1, we can simply find something that has self-conjugate property. And such a polynomial can be found using a basis of half dimension, of dimension n by 2. Okay. So this is basically a distinguishing attack in general, except for some worst-case keys where the adversary has control over the symmetries. So what we observed is that instead of exploiting the symmetry of the ideal, we can also exploit the symmetries of the ring element to transform this problem into a new unique SVP problem in lower dimensions. And then we do lattice reduction step to recover this unusually short vector. Okay, how to start with? So we also consider this capital omega 2 T1, which is the largest subset of capital omega T that remains invariant under the transformation of inverses. Then we know the evaluation of f both at little omega and little omega inverse. Thus, we can compute the sum and the difference of this evaluation. And this gives T1 distinct evaluation of a new polynomial, psi plus and psi minus, which is defined as the sum and the difference of this hidden polynomial f with its conjugate. The idea is to find this psi plus and psi minus using lattice reduction algorithm in a lower dimension lattice, and then do linear algebra to recover the hidden polynomial little f of x. Okay. So for any ring element, if the new polynomial psi plus and psi minus can be generated by a basis of order n plus and n minus respectively, where n plus is the seal of n by 2 and n minus is the floor of n by 2. This is because the mapping x to the power I to x to the power I plus x to the power minus I in the interval 0 to n minus is well defined. Then by linearity, we can generate two different bases to generate psi plus and psi minus of approximately half the dimension. Also, if fx has coefficients in the interval -1 to 1, the new polynomial psi plus and psi minus has coefficients in the interval -2 to 2, and so we can expect the norm to have around square root of n plus and minus in the new representation of the basis. Okay, like in the direct primal attack, we now have a new homogeneous cis problem to recover psi plus and psi minus using the new basis of approximately half the dimension. Like before, we have a knapsack problem, and the task is to find this unique short vector problem on the kernel that is generated by this W star and W minus respectively, which is unusually short, like from the last argument. Now, since the evaluations are explicitly computed, we can just perform this lattice reduction step in parallel. Like, we don't need to wait for lattice reduction to finish and then we do the second one. So the lattice reduction can be just performed in parallel for finding psi plus and psi minus using two different lattices. Now, it remains to see how lattice reduction behaves in recovering this unique SVP problem. For that, we rely on the analysis of GN from Eurocrypt 2008, who shows that the cost of lattice reduction algorithm to recover this unusually short vector depends on the factor called root Hermite factor, which is defined as the uniqueness to the power 1 over the lattice dimension, where the uniqueness is the ratio of the norm of the second largest vector in the lattice and the unique short vector in the lattice. For our case, we know this value of lambda 1, but we don't know the value of lambda 2. But since it is a cryptographic lattice, we expect it can get as uniform as one might want. And then we can approximate this lambda 2 using the norm of this Minkowski's theorem. And I want to just make sure that with larger values of delta, it becomes easier for lattice reduction algorithms to recover this unusually short vector. Now, for our case, if we compute this root Hermite factor for the direct primal attack and for our attack, this is going to give better root Hermite factor whenever this value T1 is more than T by 4. So T1 is the number of pairs inside this capital omega T that was picked at random. And this corresponds to the weak case of the PV knapsack problem. One thing to note here is, given this capital omega T, you don't need to run the lattice reduction experiment first. You can just check this number of pairs that has arrived in the set by computing T1 using all the pairs that has formed little omega and little omega inverse in the set. So weak keys are identified easily. Like, given an instance of the PV knapsack problem, the adversary knows exactly like this is a weak instance or not. Okay. Now it only remains to see how the distribution of inverse behave. For that, we use standard combinatorial argument. In the numerator, the first part belongs to the way you can choose the T1 pairs, and the second and the third in the numerator belongs to the way of choosing the unpairs from the remaining part. And the denominator is the way you choose T elements out of n. Now, when T is n by 2, the expectation of T1 is going to be T by 4. And this is what I have in the plot for a parameter set used in the literature. For example, when n is 512 and t 256, this peak belongs to this t by 4 value. So if the crypto system is used by many users, some of them will pick keys which are vulnerable to our attack. And that gives the weak key thing into account of the PV knapsack problem. OK, we used our attack on some concrete parameters that was used in the literature. For example, with the 2014 proposal, one of the parameters set that has N577, T280, and Q743177, we could able to solve the problem in reasonable time. So to understand like how the direct primal attack works, we use the LWE estimator. And if we believe the LWE estimator gives us right accuracy, so for this parameter, the direct primal attack would have give 52-bit security. But every non-negligible fraction of the keys that we have solved is much below than the bits operation claimed from the direct primal attack. For example, we also tried some experiment on the 2018 proposal with N512, T256, and Q2 to the power 16 plus 1. So the direct primal attack gives 54-bit security using the LWE estimator. And we could able to find some instances of it which has a non-negligible probability in reasonable time. OK? So last thing, why don't we use the symmetry of higher order is because if we use symmetry of higher order, the evaluation points are reduced too much on the average. For example, one of the proposal which takes n-1 is 0 mod 3. The number of triples for probability 2 to the power 26 goes to 42, where the number of pairs would have been 92 on the average. In the first case, we solved the problem in approximately 6 hours. And for the second, it took approximately 5 days to solve the same problem. So even the lattice dimension is small. It's harder for the lattice reduction algorithm to recover this unusually short vector because the volume gets much smaller. So that's what I had in mind. If you want any question, feel free to ask.
Thank you very much for the talk. Is there any question in the room? Let me just check on the chat. Yeah, neither on the chat. No, in that case, actually, I exactly wanted to ask what was the higher order generalization of your work like since you were descending to the totally real subfield, but you already answered it in your last slide, so
Yeah.
it doesn't work.
Yeah.
In that case, thank you very much for the talk, and let's thank the speaker again. Okay, for the second talk of this session, it's our pleasure to receive Guillaume Mureau, who is going to present cryptanalysis of the rank 2 module leap for totally real number fields. So, Guillaume, the floor is yours. Thank you very much.
Thank you for the introduction. So, as Thomas said, it's a joint work with Alice Pellemari, my PhD advisor, Georges Piatchok, and Alexandre Wallet. And we did the first cryptanalysis of a new problem, a new lattice problem called the module lattice isomorphism problem. So more precisely, I will present you an algorithm solving this problem in the particular case of rank 2 modules over totally real number fields. So I will give explanation on these words. First, I will present you the definition of the problem and then the algorithm for solving it. The first motivation for this work, is a paper from 2022 by Duca, Postlethwaite, and Pules, and Van Voorden, in which they introduced module leap. And they used it to build Oak, which is a signature scheme. So it was submitted to NIST's additional call for signatures. So Oak is based on a module leap problem over cyclotomic fields. And it's really efficient and compact. It takes advantage of the module lattices, which are a compact way to represent high-dimensional lattices. And so in this talk, I will present you a heuristic algorithm, which is polynomial time, in many cases, solving module leap for modules which have rank 2 and over totally real fields. So let me emphasize that this doesn't break Hawk, because Hawk uses cyclotomic fields, and cyclotomic fields are totally complex fields, which is quite the opposite of totally real fields in which the attack applies. So first of all, let me define leap, the lattice isomorphism problem. Given two lattices which are isomorphic, so that means that one lattice is a rotation of the other. The problem is to recover the rotation. For example, in rank 2, we are given a basis B1, B2 of a first lattice. We take a rotation of this lattice, rotation which is unknown, but we are given a second basis, B1 prime, B2 prime of this rotated lattice. So the goal is, given this basis, to recover the isometry. And actually, the state of the art for solving this problem requires to compute potentially many short vectors in both lattices. So this is related to SVP, the shortest vector problem, which is well known to be a hard problem. So in module leap, we use module lattices. So formally, a module lattice is any finitely generated module over OK, the ring of integers of a number field. For example, let me take k power of 2 cyclotomic field, so q of x modulo x to the 2 to the k plus 1, then its ring of integers is z of x modulo the same polynomial, and if you're not really comfortable with number fields, you can just take k to be the field of rational numbers, and then OK is the ring of integers. Easiest example of module lattices are rank 1 module lattices, which are fractional ideals. In rank 2, for example, we can take 2 copies of the ring of integers. This will be a really important example for the following. And more generally, a module lattice looks like this. So copies of AI, fractional ideals, times of vectors in some power of k. This is called a pseudo-basis. So to keep it simple, I will not manipulate pseudo-basis. I will only consider 3 lattices, so we'll have basis. And so module leap is the same problem as leap, but we consider module lattices, and we want to find isometries which also preserve the algebraic structure. The state of the art, so this is a new problem, and the state of the art is basically to completely forget about the structure. You just embed your module lattices in some Euclidean lattice in R to the DL, and solve it as a non-structured leap instance. So let me define module leap on some motivating example. I took K a number field and M 2 copies of the ring of integers. I fix the notation X star is transpose and conjugate. So this is maybe a bit technical, but you only have to keep in mind the final statement of this slide. So we say that a module M prime is isomorphic to M if there exists a matrix O such that O star U is the identity, so think of a rotation, and such that M prime is the image of M by O. In terms of basis, so if we are given a basis B prime of M prime and B of B, and B of M, there exists a matrix U, invertible with coefficient in OK, such that B prime is equal to OBU. And we could define module leap as the problem of recovering over O or U given B and B prime, but instead we prefer to move to quadratic forms. So to a basis B, we associate its Gram matrix. So to B, we get B star B, and B prime star times B prime. And if we get a relation B prime equals OBU, so we have isomorphic module lattices, in terms of Gram matrices, we get congruent Gram matrices, so a relation of the form G prime is equal U star times G times U. And for example, taking the easiest basis of the module OK plus OK, so the basis identity, the gram matrix associated is also the identity. And we get this module leap problem, which is given G prime, a gram matrix which is congruent to the identity. The problem is to recover all U such that G prime is equal to U star identity U. So basically, you can just think of it as the problem of factoring gram matrices. Let me do the link with Hawk. So in Hawk, K is a power of 2 cyclotomic field, which is not a totally real field. The secret key is the secret basis of the module OK plus OK, and the public key is the associated gram matrix. So to recover U from G is exactly what we define to be a module leap instance. And actually, any solution, D to V star V is equal to G, is actually a key recovering for Hawk up to some automorphism. So now let me present you the algebraic attack in the case of a totally real field. From now on, I suppose K is totally real. The most interesting example is maximal totally real subfield of cyclotomic field. So fields of the form Q generated by zeta plus zeta minus 1. And let me take a secret basis, U, with coefficients in OK. So I recall that the goal is to recover U from its gram matrix. And if you expand the matrix product, what you see on the diagonal elements, so you get elements A times A bar plus B times B bar. But since K is a totally real field, the conjugation acts trivially. So in fact, you get sum of 2 squares on the diagonal. This is the first observation. And now see that a sum of 2 squares, so for example, A squared plus B squared, you can rewrite it as A plus IB times A minus IB, and this is exactly the definition of a relative norm. This is the relative norm of the element A plus IB, which lives in the quadratic extension K of A. So the main idea is to solve relative norm equation. If we are able to compute all solutions to some relative norm equation, we will be able to reconstruct A and B, and same thing with the last coefficient of the gram matrix, we can get C and D. So we get exactly the secret key. To solve norm equation, we use an algorithm by Hogravegram and Sidlow. As input, it takes an element Q in OK, and the prime factorization of its algebraic norm. This is a really important data. It will output all pairs of elements in OK, which are solutions to the norm equations. And it runs in time polynomial in the degree of the field, the logarithm of the algebraic norm to the R, where R is the number of distinct prime factors of the ideal generated by Q. So if you don't know about prime factorization of ideals, you can just think of K is equal to the field of rational numbers. Then Q is a rational integers, and R is exactly the number of distinct prime factors of Q. In average, R is not too big, but it could be in the worst case, and we want to avoid these cases. So we added a randomization step to guarantee norm equations where R is equal to 1. One advantage is that we know the prime factorization of this algebraic norm. A drawback is that now the attack is heuristic. We need some assumption to estimate the probability to get a new input after randomization, a new input as we want with R is equal to 1. And so the conclusion of that is that we get norm equations which are easy to solve. So let me explain how we can randomize the input. We use Gaussian sampling. So as input a gram matrix and some sampling parameter, it will return a module vector in OK plus OK, which follows a discrete Gaussian distribution according to G. We use it 2 times to get a matrix V. Suppose that this matrix is invertible. You can compute a new gram matrix, V transpose GV. And we do it until the diagonal coefficients generate prime ideals. So we need a heuristic for the probability of success. The we did an assumption in the paper. So this is based on numerical experiments, but also theoretical results. It involves the distribution of prime ideals, and in particular a quantity called ρk, which is the residue of some function of the field. So the final statement for the module OK plus OK in the maximal totally real subfield of some power of 2 cyclotomic field is the following. There exists a heuristic algorithm solving module leap on input G in expected time polynomial in so this ρk, the degree of the field, and the size of the input. And for our experiment, so for maximal totally real subfield of power of 2 cyclotomic fields, the ρk was always really small. Here are some running times. So the full attack is available on our Git. We implemented it in Sage. We also implemented in Sage the Gen3 seed law algorithm, which is the main tool in Hograve-Graham seed law algorithm for solving norm equations. More generally, we can define module leap for any number field and for any module lattice. Module lattices of any rank, and it looks like something like given 2 gram matrices G and G prime, which are congruent, find all matrices U, satisfying G prime is equal to U star GU. The attack I just presented works for any rank 2 module lattice over any totally real number field, but in general, there is an extra complication. In general, during the randomization step, we can hope to get elements which generate prime ideals. This is because all the new elements we construct, they always lie in a common ideal, which is the ideal generated by the squared norms of the module vectors. And if this ideal is non-trivial, we have no hope to get prime elements. But for example, I just presented, so OK plus OK, this ideal is actually trivial. And the general statement is the following. So for any totally real number fields and rank 2 module, we take as input G prime, a gram matrix which is congruent to G, and we can solve the problem, so recover all the congruence matrices. In expected time, something polynomial in ρk, the logarithm of the discriminant of the field, the size of the input, everything to the r plus 1, where r this time is the number of distinct prime factors of the ideal generated by the square norm. And we have to add the time to factor the algebraic norm of this ideal. So to conclude, when K is a totally real field and M is a rank 2 modules, we saw that module leap reduces to solving some relative norm equations in number fields, which is a quite classical problem. But we introduce a randomization to keep easy instances. And under some heuristic for the randomization, we get a polynomial time, in many cases, algorithm solving the problem. So I would like to conclude with some open questions. It would be nice to see if this kind of arguments applies for higher rank modules. And also, keeping rank 2, we would like to make something similar for cyclotomic fields. So thank you for listening, and here is a QR code for the full article.
Thank you very much for the talk. It was great. Do we have questions in here?
So you're looking for prime ideals. Would it also work with a totally ramified ideal, or do you need prime ideals on the diagonal?
So the diagonal elements of the gram matrices, we want them to generate prime ideals because this reduces the complexity of the algorithm.
Distinct prime factors. So if it was ramified, that would also be.
Oh yeah, you mean it could be a power of a prime ideal?
Totally
yeah.
I don't know if that just never happens.
Yeah, it could be, but we did an assumption to get exactly prime ideals. Yeah. Yeah, thank you for the question.
Is there another question? Yeah, if not, I have a small one. So you're introducing this randomization, so you have this kind of superfluous factor which depend on the residue at one of the zeta function, which I assume is complicated to evaluate. Do you think it's possible to get rid of it completely, or is it just like an obstruction?
Well, actually, we have current work on it. So the randomization is just here to guarantee norm equations which are easy to solve, because we need, in the approach I presented, we need all solutions, but actually we proved that we need only some specific solutions. We know where to locate them, so the randomization is no longer needed, and the approach is no longer heuristic.
Okay, thank you very much.
Thank you.
Sorry, I have to wait for the slides.
Yes, can we have the slides, please?
Sorry about that.
Okay, thank you very much. So for our third talk, we're happy to listen to Amaury Pouli, who is gonna talk to us about the probable dual attacks on LWE. So Amaury, the floor is yours. Thank you.
Thank you for the introduction. This is a joint work with Yixin Shen, who is in the audience today. So I'm just going to assume everyone knows that LWE is a very fundamental problem for lattice-based cryptography. So I'll just use this slide to remind you of our notations that I'll use in that presentation. As usual, n is the dimension of the secret, m will be the number of samples, because this will be relevant. We have an error distribution chi-e on the errors. We always work with a prime number field, and then we have some secret S that we are trying to recover, given a sample of the LW distribution, which is defined as usual with sample matrix A uniformly at random and a noise vector according to the distribution chi-e. So in the paper, we don't make any assumption about the error distribution of this secret. For example, the secret doesn't need to be small. However, we do have a small assumption on the number of samples. For the attack to work, we need twice the number of samples as the dimension, and I'll mention at the end why and how we could probably avoid that. So the motivation for that work is a controversy that happened recently about U attacks, and I'll try to explain briefly what it's about. I don't want to do the full history of U attacks, so the two most relevant papers for that particular thing are this 2021 paper by Guo and Johansson, where they describe a dual attack that produces many short vectors with sieving, and they also use this discrete Fourier transform trick to massively improve the complexity, and they suggested this modular switching technique that could be used to get a really efficient attack. But at this point, this was quite heuristic, I would say, until this 2022 report by the Mazov group, where they essentially took this attack, did the modular switching, and formalized this completely. The paper is very long, it's very technical, and at the end, he claims some comparable results with the best primal attack in some certain parameter regime. So by this point, it seemed like some dual attacks could be competitive with primal attacks. However, the correctness of the attack relies on a number of statistical assumptions, which by that point were getting fairly long and complicated. So it was natural to ask whether they actually hold. And this became an interesting question because of this claim that they are really efficient. And this is what Duca and Pouls did in their 2023 paper, where they took Mazov key statistical assumption, they simplified it, and they tried to analyze it. And the conclusion was that under the choice of the parameters that Mazov uses in their paper, then this assumption does not hold. And they conclude from that that the result, or at least complexity claims by Madzov, are at the very least unsubstantiated, and the attack might even not work at all. Now, an open question, and I'll go back to this at the very end, is whether this simplified assumption that they analyze in this 2023 paper is really equivalent to the Madzov key assumption. And I think that's really the main issue there, whether they're actually proving the attack is wrong or not. So what we did in the paper is that we also tried to analyze dual attacks, but we tried to sidestep the whole controversy. So what we did is that we simplified a little bit the dual attack, and we proved it completely correct. We did the full non-asymptotic analysis, and there's no assumption whatsoever for the correctness. So that way, we don't have this problem about this heuristic assumption. And a side effect of this is that it makes it completely clear for which parameter regime the attack works, which I think is something the previous papers didn't do that well. And I'll explain why this turns out to be nicely complementary with the analysis of this 2023 paper. And how do we sidestep the whole thing? Well, we go back to using discrete Gaussian sampling instead of sieving in order to produce short vectors. And I'll explain why and how we do that. Now, the paper also has other contributions. There's a quantum version of the algorithm that has a non-trivial speedup based on ideas from this unpublished draft by Albrecht and my co-author. And what's nice, I think, in the paper is that we improved the analysis of this discrete Gaussian sampler by Wang and Ling, specifically for a case of BK-reduced basis, which is how we get a better discrete Gaussian sampler compared to what you would expect. And finally, we also have some complexity estimates, but I'll present them at the end. You have to take them with a grain of salt, definitely. Now we get to the unfortunate technical slide of the presentation, because I'll actually try to explain a little bit what's a dual attack and how it works. So I apologize for the technical slide. So remember, we're given an LWE sample, AB, and B is AS plus E. We don't know S, we don't know E. So the dual attack usually proceeds by splitting the secret into two parts. There's the guessing part that we're trying to recover, and there's the dual part, which we'll try to make disappear. And so we split the matrix A according to this secret splitting, and we introduce this lattice, which is the image of the A dual together with all multiples of Q, which is often called construction A. This is completely standard. And the next step, which I'll explain in the next slide, is that we somehow assume that we're able to build this function f that, given a vector t, any vector t, somehow measures the distance between t and the lattice L. So this might not be the most canonical presentation of the attacks, but let's assume we can do that. Then the attack actually becomes quite straightforward, at least for correctness. We make an educated guess on the secret, and we just evaluate this magical function f on B minus our guess, essentially. And what happens is, because L is constructed from A dual, then the dual part of B completely disappears, and we're just left with the error plus the guessing part. So we just have to understand what happens in the case of a good guess and in the case of a bad guess. So very briefly, in the good guess, it's very simple, because the guessing part completely disappears as well. So we are left with measuring the distance between the noise vector E and the lattice L. But the error is usually quite short, so we're really literally just measuring the norm of E. Now, what happens in a bad guess is more involved. So very briefly, I'll just claim the following. If you have a matrix A, then for most choices, what will happen is that when you take the vector E and you add up this non-zero guessing part, then the distance to the lattice L is actually longer than the norm of E. And in that case, because f measures the distance, you can immediately see that f of this guess will be larger than the image of a good guess. And so the conclusion, even if you're completely lost, now you just read this, the summary is that if the error E is not too large, and for most choices of A, you can recover the secret just by evaluating the function f on all possible guesses, take the maximum, and you're done. Great. Now we're done, except we're not, of course, because all of this relies on the magic score function f that we need to construct. And remember, this function needs to measure somehow the distance between its argument and this lattice L constructed from a dual. And the usual way to do this, and I'm definitely not going to explain why that works, is to compute many short vectors in the dual lattice of L, and then to compute this sum. And there's good reason why this should work. Again, not going into that. What's more important for our purposes is to understand that the way we generate the short vectors has a massive impact on how we analyze this later on. And the usual way to do that, this is done in virtually all the attacks, is you just reduce the basis with BKZ, and then you sieve in the lattice L. In fact, if we're more precise, you need to sieve in a sublattice of the lattice dual, which makes it even harder. And the result is that this is very complicated to analyze, and that's a major source of issues in the proof of Madzov. And that's why they need this statistical assumption that everything goes well. Everything is independent, everything is nice. As I said at the beginning, we want to sidestep this, so instead, we also reduce the basis using BKZ, but then we use a Gaussian sampler built from that basis so that we avoid all the problem. Why is it the case? Because when we use the Gaussian sampler, then the behavior of that function f is well understood. We've known since our NOV and regf that this really does measure the distance to the lattice, hiding a lot of stuff under this approx equal, and rho of s is essentially the Gaussian function. So this is nice. It works, except for a slight problem, which is it's super inefficient if you do it the naive way, which is probably why no one is using Gaussian samplers to solve dual attacks. I'm not entirely sure about that. So hopefully I can convince you that this is not the case. And for that, I just need to say a few words about Gaussian sampling. When we sample from the discrete Gaussian distribution, we need to choose the parameter s, like the width. And we know that if the width is super large, then this is super easy because it's almost like a continuous discrete Gaussian. We round and we're done. If s is very small, this is super hard because all the mass will be on the shortest vectors, so we're essentially solving the SVP. And somewhere in the middle, there's this thing called the smoothing parameter, which is when the discrete aspect of the Gaussian starts to kick in, and it starts to get hard. So whether we can sample from that efficiently is really an open question. And unfortunately, for dual attacks, well, the smaller s is always better. And ideally, if we are under the smoothing parameter, it's better in our attack. Don't have a good explanation for why, but the numbers just show that, we show that's the case. So if you did it the naive way, you would run BKZ, and then you would use, say, a Klein sampler. And in a Klein sampler, the good thing is that you get a sample in polynomial time, always. So this is very efficient, but the s depends on the basis. So to get a smaller s, you need to reduce it more, which is costly. And independently of how reduced the basis is, s will never go below the smoothing parameter. And this turns out to be not good enough in our experiments to get a good complexity. So instead, we used another sampler by Wang and Ling, and this is more of an advertisement for their paper, really, because here, the complexity and the value of s depends on the basis. There's no constraint on s. But now, it may not run in polynomial time. And in particular, for us, there was a very interesting regime where s is slightly below the smoothing parameter, and now the sampler runs in exponential time. But it's not actually a problem for us, because if the exponential is not too large, it's worth the time spent to get better vectors and a tighter analysis later on. However, I'll just point out that the generic complexity bound that they give in their paper is not good enough for our case. So we improved it specifically for our case because we know the basis is BKZ reduced. So using the geometric series assumption, we're able to actually derive a better complexity bound. And by doing all of this, skipping many details, of course, we are able to show that our simplified dual attack works for most LWE samples. So again, most matrices A, most choices of E, as long as E is not too large. And not too large means at most half the length of a shortest vector is in this lattice LQ of A. So that's the construction A from the matrix A. And just a side note here, it actually depends on the whole matrix A and not just the dual part of A. which might be slightly counterintuitive. Now, as I said at the beginning, we actually get a nice complementary regime with this 2023 paper by Duquesne and Pauls. So in their paper, they introduced this thing called the contradictory regime, where they showed that if you go too far, then there's no hope to solve dual attacks, because essentially you would be distinguishing things that are known to be undistinguishable. And their regime, in our simplified case, corresponds to E being larger than lambda 1 of LQ of A, which if you think about it, 5 minutes is completely clear it cannot work, because if the error is too large, then the secret is ambiguous, like you cannot recover it even in theory. So the takeaway for me from all this provable analysis is that now, with their work and our work, we have a fairly good understanding of when a dual attack, in our simplified case, again, works, and we cover most of the parameter range. So the only thing left is this small gap between half of the lambda 1 and lambda 1. And here, I believe that it should work up until lambda 1. It's just a deficiency of the analysis. It would need to be a bit more refined to make it work. But there's no theoretical reason why it shouldn't work. And now we get to the complexity estimates, because of course, we've proven that the attack works, but this is not so interesting in its own if the attack is super inefficient. So I'll try to convince you it might be made efficient. Now, of course, the problem is we don't use modulo switching because we simplified the attack. And we know that's a crucial element to make it efficient. So the attack just cannot be competitive in its form. And indeed, if you run the numbers, they're absolutely terrible for all versions of Kyber. But we expect that. That's not an issue. So what we try to do is that we try to estimate what a hypothetical extension of our attack together with modulo switching would look like. Of course, that's an exercise in, I don't know, futility or dangerousness, depending on how you see it. And at the end, we get numbers that are extremely close to the original claim by Matzov, which is very promising, but of course, all of this relies on, well, nothing. It's not proven, and it's probably too optimistic. But the main takeaway from this, in my opinion, is that it validates the entire approach, because if, for example, the Gaussian sieving had been too inefficient, then it would be a bottleneck, and you wouldn't see those numbers. So it shows that actually this probably can be made efficient, even if we don't reach those crazy numbers. Now, before concluding, I want to go back to the initial issue, which was this controversy regarding whether this 2023 paper by Duquesne and Pauls really proves that Matzov is incorrect. So the answer is I don't know, but I'll try to convince you the answer is not clear. So remember, we're given an LWE sample, AB, and I said you can recover the secret part by just evaluating the function f on all those points, which they call targets, so all those guesses, and taking the maximum. And here f is the function f, which depends on your choice of dual vectors, which is very important. Now, if you try to write down precisely what would be the Matzov key assumption, it would look something like this. You have to show that with high probability over the choice of your dual vectors, the estimates of a good guess, so f of e, is larger than the estimate of a bad guess. And what is a bad guess is e plus a guess times anything non-zero integer in our case. And well, this is not very easy to analyze because first of all, it depends on a guess. So now you've got something else to analyze. This is not nice. And also e is on both sides of the equation. You've got dependencies. It's a bit of a nightmare, really. So what they did in their paper, I think, is that they tried to take that and simplify to something that's maybe easier to analyze. And they came up with this, where on the left-hand side of the equation, you still have f of e, so the good guess. But the bad guesses are replaced by just a uniform vector in the fundamental domain of L. And later on, they themselves and another group who have a paper at this conference, actually, so I hope you saw their talks, analyzed specifically the distribution of f of t, among other things, when t is a uniform sample of the fundamental domain, and x come from sieving in the lattice. However, I just want to point out that it is not clear to me that assumption number 2 here is really equivalent to assumption number 1. Because in fact, if we look at our own proof of the paper, it wouldn't work for equation 2. It really uses the structure of the targets that are in some sublattice that depends on a guess. So for me, it's clear they're not equivalent, but it doesn't necessarily mean that the analysis by Duque and Poole doesn't imply that Mazoff is wrong. So I'll just leave it as an open question. I think it would be very nice to understand that better. So in conclusion, as I said, the main takeaway is that we have, I think, now a strong foundation with this paper and other papers on provable dual attacks with no assumptions whatsoever, which I think is nice. And hopefully I've convinced you that this Monte Carlo Markov chain sampler is worth having a look. It's not ours. And the main purpose of this was really to simplify the proof, which I think we were quite successful at. We have promising complexity estimates and the quantum algorithm, also with no assumption. And of course, the biggest open question is, can we analyze modular switching to make the attack efficient? Modular switching does not play nice with our proof, well, with anybody's proofs, really. So I think this other technique of using coding theory to reduce the dimension by this unpublished draft of Carrière, Chen, and Tillich is much more promising. I mentioned the gap already between the working and the contradictory regime. And finally, I mentioned at the very beginning, we did twice the number of samples at the dimension. This is not great because in practical settings, you probably only get as many as the dimension, not more. So the way to solve that is classical. You just work in a slightly different lattice. And now you don't have dual vectors, you have something else. And yeah, we didn't make the proof for that. It would probably be slightly more complicated. So we'll leave it for another paper. Thank you.
Thank you very much for the talk. Do we have any question in the room?
Hi, thank you for the talk. I was wondering, you use the GSA. I was wondering if you have a feeling for how much the HKZ tail would impact the efficiency of the attack.
Yeah, fair question. We've actually started to look into it, but I don't have the answer yet. My feeling is it makes no difference because it's really, I think it's really the beginning that counts. But again, that's definitely something we're looking into. We've started to want to run some simulations and see if that actually makes a difference because it's a big question.
Thanks.
Hi, thank you for the very nice talk. My question is, in your presentation of your results, you say that it worked for most matrix I. I was hoping you could be a bit more precise, in particular, in which case doesn't it work?
Yeah. Okay, do I have a slide where I can explain this easily? Yes, there, more or less. So what happens is, in the bad guess case, we need to argue that the distance between this A guess plus E is far from L. But you can see, for example, that if A guess, all their vectors are in L, then obviously it's completely wrong. So for most A means most matrices of A will have A guess sufficiently orthogonal to L. That distance will actually make you further away from L and not closer. And this is indeed true for most choices of A.
Have you assessed the probability that this happened?
Yeah, it's exponentially close to 1. So it's really not an issue. I'm not lying about the most here. It's really, literally most of them.
I wasn't thinking we were late. Thank you very much.
Thank you very much. If there is no more questions, we can thank the speaker again. And for the final talk of the final session of this Eurocrypt, we're happy to have Pierre Briot, who is going to show us a practical attack on all parameters of the DME signature scheme. Pierre, the floor is yours.
So hi, thank you. So this is joint work with Maxime Brault, Rail Turner, and Daniel Smith-Toney.
And I will present you, as you said, a practical attack on all parameters of the DME signature scheme. So DME is one of the candidates to the call for additional signature schemes, which started last year. So here I wrote new with quotation marks because it is in fact the descendant of a scheme which was submitted to the former call for KEMS and signatures back in 2017. So it's a multivariate scheme, but we'll see that the design is essentially ad hoc. And a clear motivation for our work was also is surprisingly good performances. First, it's very compact. You have the sizes here for the security level 1. It's also very efficient in terms of both signing and verification time. But unfortunately, in this paper, we give a practical recurring attack. We can easily break all parameters of the scheme. So I'll start by describing the construction because, as I said, it's very particular and we really need to understand it to understand our attack. So DME is a multivariate scheme, so the public key, as usual, is a set of polynomial P1 to Pm over a final field AFQ in n variables. I will also view this public key as a map from FQN to FQM. And a signature sigma is essentially a pre-image of our message under this map so that verification boils down to computing the map. But here, DME is not a standard multivariate scheme, I would say, in the sense that first, our polynomials are not quadratic, which is usually the case. Here, the polynomials have essentially exponential degree. And also, the number of polynomials and variables is extremely small. I have m equal n equal 8 for all security levels. In general, the value of m and n is mostly like linear in this security level, so that the MQ problem is hard. And here, what is a function of the security level is the value of Q. It's exponential in this parameter. So the main feature of DME is that it is a construction with several rounds. So you have 4 rounds Ri. So each of them is made of a nonlinear map that I will call an exponential map, a linear map Li, but which is of a very specific shape, and I will come back to it. And finally, an addition of constant. So all these components are private for all my rounds, but if I know them, I can easily invert my public key to compute signatures. So the exponential map works over FQ squared, degree 2 extension field. So very often in the talk to 2 small field elements, x and y, I will associate them one big field element, x plus y, just in the same way as for 2 real numbers, you have 1 complex number. And by doing so, I get this linear isomorphism phi. It maps a state of length 8 over FQ to a state of length 4 over SQ squared. And once I am over this extension field, I apply this second EA map. So how does this map work? So here, A is a matrix of size 4 which contains exponents. First, I will raise my components to these exponents, and then I will multiply them together. And so here in this equality, what will be important is that each coordinates correspond to one row of my matrix A. For example, the first coordinates correspond to the first row, the last coordinates correspond to the first row. So by construction, these maps, they have some properties of the underlying matrices for both composition and inversion. So here the map is not fully invertible, but its invertible is to restrict the input domain. But what will be more important in our attack is the shape of the matrices which are concretely used in the scheme. So here are they. So the first one is just the identity. If you prefer in your first round, the first exponential map is trivial. And my other matrices, they are also very special. So first we see that they are extremely sparse. And also all the non-zero entries of powers of 2. So we know that these are powers of 2. We know their position in the matrices. We simply don't know the value of the exponents. And I recall you, these are powers of 2, but these are also the exponents to which we have to raise the components of our state. So we have a double exponentiation here, and this is basically what gives the name of the scheme, because DME stands for a double matrix exponentiation. And finally, I come back to my linear map. I said it was special. It is special here in the sense that it will only act on pairs
of consecutive coordinates. So instead of having a general invertible matrix of size 8 to represent my map, I have a block diagonal matrix where each block Lij here is invertible of size 2. And the particular shape of this map is also what contributes to the efficiency of the scheme. So now I will move on to our attack. It will be a key recovery attack. Here we are going to recover an equivalent key. So this means a composition of possibly different ones, but from which we can still recover the public key. And our strategy was to do it round by round. And what I will explain you today is how essentially we recover the last one. So for this, I will describe the main ingredients. And especially the main technique was to work entirely over the extension field. So for that, we consider a big field version of our public key, P hat. So P hat is a set of 4 polynomials in this quotient ring. So we obtain it by composing the genuine public key P by a linear isomorphism. So here I wrote with phi. It's not a big restriction to do that, trust me. And by doing so, I get a computation path you see on the top of this ugly picture that everything is over fq squared. And in particular, I can write now my public key as a composition of rounds which are entirely over the extension field. In their definition, on the bottom right, we recover the EA map of before, but this time we have a linear map and an addition of constants which are also over the extension field. And so the advantage here is that my new linear maps, they have a much nicer expression. So why? If I come back to the previous one, it was acting only on pairs of 2 consecutive coordinates, and also my isomorphism phi also takes 2 consecutive coordinates over the small field to map them to one big field element. And if I combine this, I can see that my new linear map will only act component-wise. So for each component j, I have a linear map Lij hat, which will act over fq squared. So in other words, I have secret q polynomials here, which contains only 2 terms to represent that map. So why 2 terms only? This is because I was working in this quotient ring. Okay. And so the conclusion of this is that now I can focus on a scheme where the components will only be mixed within the exponential maps, and so it will be much easier to study. So what we'll study precisely is now the monomials which are present in the intermediate states. So here I represent the intermediate states that I obtain after applying the east round of my scheme. So obviously this state is private except for the I equals 3, because for I equals 3 we recover the public key. And so to study these monomials, I will introduce a definition. So what I call the orbit of a monomial mu is the set of all monomials I can obtain from it by raising one or several variables to the power q, one or several times. And this set will be finite because I will consider all the representatives of my monomials in this very same quotient ring. So in particular, I cannot raise to a power of q endlessly. So you have a simple example when mu is equal to x1 times x3 to the 5. You see that indeed this set is finite. And the nice thing with this notion is that the monomials that are present in my polynomial, so for all indexes I and j's, the set of monomial present in G, J, I is always a union of disjoint orbits. Okay, so why is it true? Well, it's true after applying the first round on my initial variables. On the first round, I recall that there was no non-trivial exponential map. So after the first round, I get q polynomials with a constant term. So essentially, I have the orbit of xi and the orbit of the constant monomial. And this property is also preserved by addition, multiplication, and raising by a power of 2 here. And multiplication and raising by a power of 2 are the only operation which appear within my exponential maps. So in particular, we see that this property which will be preserved at each step of my computation. But unfortunately, in my secret polynomials, these orbits are also unknowns. But there is still something we can know here, and for that, I will introduce some notation. So for an element x modulo q squared minus 1, an exponent, I will consider x bar, which is its smallest positive representative. So for a monomial mu, which is secret, I can associate it with a set of 4 integers. And so there is something I know about these 4 integers is the Hamming weights of their binary decomposition. So in short, this is this quantity in blue. And now I want to explain to you why we know this quantity. So first, this quantity will be the same for all monomials which are in the same orbits. This is precisely because each of them can be deduced from one another by raising some variables to the power of q, and I recall you q is the power of 2, so the power of 2 will not change this Hamming weight. So for the same reason, if I come back to my exponential maps, the powers of 2 which are in the matrices will not change these Hamming weights, and in fact the only way the Hamming weight can change is by multiplication between different components. But in my secret matrices, I perfectly know the non-zero entries. So I know which coordinates will be multiplied together, and in this way I can deduce the Hamming weights from the beginning to the end of the computation. And in particular, there are only 3 rounds, so things will never become complicated. So based on that, our strategy was the following. So we start from the Hamming weights that we have found by this analysis and the public key. And by doing so, we can easily deduce the monomials which are present in the state before applying the last round. So here there is no cost, it's just a formal analysis. And by doing so, we can also obtain some partial information on the last exponential maps. So at this stage, in my intermediate state, what remains unknown is the set of coefficients. And so our strategy to find these coefficients was to model this problem of finding them by polynomial equations. So for the last round, in particular, we had to solve 1 bilinear systems and 2 linear systems. So in these systems, the variables are precisely the unknown coefficient I'm looking for, and the scalars are the monomials that I have just retrieved by my Hamming weight analysis. So finally, I will show you what the bilinear system looks like. For this, I have to come back to the definition of the last round. So in this equality, in this equality on the left, you have the 4 polynomials which are the inputs of the last round. So I just simplified the notation. And on the right, you have the inverse of the last linear layer. It also contains 4 polynomials. And now what I'm going to do is exploiting the particular shape of the matrix A3. So more precisely, I will exploit the fact that in the second and the third row, the non-zero coefficients appear at the same column. And so I recall you, focusing on these 2 rows in my matrix is the same thing as focusing on the second and the third component in my equality. So by doing so, I get these 2 equations. So on the left, I have a product of 2 secret linear forms. And on the right, I have replaced the unknown polynomials by introducing their secret coefficients. So here, AI, BI, and DI are just scalars. So there is something I will not detail, or if you have questions, I can come back to it, is the partial information that we have collected on the exponential map by our Hamming weights analysis allows us to assume that the 2 powers of G4 are equal. So by doing so and by adopting simpler notation, I end up with these 2 equalities at the bottom. So I have created a common factor G. And my bilinear system will directly come from that. So more precisely, for each monomial, I will match the 2 coefficients which appear in front of this monomial on the right and on the left and on the right. And I do this for each monomial in the equation and in the 2 equations. So the equations are bilinear precisely because I have a product of secret linear forms on the left. And the system is also overdefined. I have more equations than variables precisely because I have created this common G factor. So as an example, for the security level 1, I have to consider a system with 48 equations and 17 variables. And in fact, by studying the variety of this system, we can even fix some variables, and fixing these variables still allows us to recover an equivalent key. So we can show that this specialized version of the system is trivially solved by Grosvenor basis. We never go at degree higher than 2. And by using the solution to this system, and if I come back to my first and fourth components, by applying the same analysis, now I end up with linear systems. And so by solving them, I can finish the last round recovery. So to conclude the talk, I can just say that I just apply the same procedure for the other rounds, especially because the other AI matrices have the same shape, so we'll only have to consider either bilinear or linear systems. And also, it turns out that the attack is not a lot more costly for the other security levels. And this directly comes from the fact that for these security levels, I also have m equal n equal 8. In fact, the only change will be in the field arithmetic. And so even though we have broken the submission to the NIST, it doesn't mean that the scheme cannot be repaired. And in multivariate cryptography, we know that things happen when we start repairing things. So thank you for your attention, and don't hesitate if you have any questions.
So thank you for the talk. Are there any questions in the room? There is no online. Maybe I have one.
Yes.
So you're mentioning that you think, or at least tend to think that it still can be patched. Like, can you elaborate a bit more on this?
Yes. In fact, I don't know if the author of the scheme has already communicated about this publicly, but he communicated at least to us how the scheme could be patched. It's like we see that these two polynomials over the small field, they map to somehow one polynomial of the big field. So there is something quite standard in multivariate cryptography is you would like to remove one of the polynomials of the public key, and the very same attack would not work. So this is like, it's called the minus modification in multivariate cryptography. The thing is, the scheme has a lot of structure, so even by applying this trick, I mean, for example, if we just remove one polynomial, there is still a lot of structure to exploit. And there is also something possible, is like, maybe, like if you think about symmetric cryptography, trying to increase the number of rounds, but I think if you increase the number of rounds by 1 or 2, the scheme is not efficient anymore.
Thank you very much. So if no one has more questions, let's thank the speaker again and thank you for attending this Eurocrypt.